In the last lecture, we have been considering a matrix A belonging to F m cross n and a matrix B belonging to F m cross 1, and we were interested in the non-homogeneous system A x equal to B. We considered the corresponding homogeneous system, which was A x equal to theta m. We had observed that the homogeneous system plays an important role in the analysis of the non-homogeneous system. And what we meant by this was the fact that a consistent non-homogeneous system has unique solution if and only if the corresponding homogeneous system has only trivial solution. Thus, the homogeneous system plays an important role in determining the uniqueness. Then the general solution of a consistent non-homogeneous system is of the form x equal to x p plus x h, where x p is a particular solution of the non-homogeneous system and x h is solution of the homogeneous system. By varying x h over all the solutions of the homogeneous system, we sweep all the solutions of the non-homogeneous system. Therefore, finding solution of non-homogeneous system has two parts. The first part, find x h, the solution of the homogeneous system, and 2, find x p, a particular solution of the non-homogeneous system. So, thus we have two parts that are going into the solution of a non-homogeneous system, and as the beginning we looked at the solution of the homogeneous system. And for this, the main strategy or the main tool we introduced was the so called elementary row operations, which we denote by EROs. There were three types of elementary row operations that we introduced. The first one, which what we denoted by Rij, it is the interchange of rows. The ith row and the jth row are interchanged in the matrix A. The second row operation we did was, to a row j, let us say Rj, the jth row, we add a multiple of another row Ri, where alpha is of course from F. So, to some row you add a multiple of another row. This is the second type of VRO we introduced. The third type of VRO we introduced was, take any row Ri and multiply it by a non-zero number belonging to F. So, these were the three types of elementary row operations that we introduced. The basic properties of the elementary row operations that are going to be useful in our analysis are the following. 1, the EROs are invertible, and of the same type. Of the same type inverse. That is, if you interchange two rows, the inverse is again an interchange of two rows. If you add a multiple of one row, the inverse is again adding a multiple of one row, and if you multiply a row by a non-zero number, the inverse is again multiplying the row by a non-zero number. So, the EROs are invertible and the inverses are of the same type. The second important property is that the EROs do not alter the set of solutions of the homogeneous system. This is a very crucial point in determining the homogeneous system solutions. The third, which we shall be using later, is that the EROs can be implemented or can be effected by pre-multiplication by an elementary matrix, pre-multiplication of the matrix A by an elementary matrix. Recall, by an elementary matrix we mean a matrix obtained from the identity matrix by applying an elementary row operation. So, if we have the identity matrix I m and we apply an elementary row operation, one elementary row operation, and we get a matrix A, then this is called an m by m elementary matrix. So, any matrix obtained from identity matrix by a single elementary row operation is called an elementary matrix. These are the simple properties of elementary row operations. Then we introduce the notion of row equivalence. Supposing we have two matrices A and B in Fm cross n, and there are EROs either of type 1 or type 2 or type 3, one type of or the other of the EROs, say O1, O2, OK, finite number of them, such that you can start from A and apply this sequence of EROs to eventually in the last stage get A k, which is equal to B, which means I can move from A to B by a finite sequence of EROs. Then we say A is row equivalent to B and we write A or B. The properties of row equivalence are very useful. One, every matrix is row equivalent to itself. This is called the reflexivity property. If a matrix A is row equivalent to a matrix B, then B must be row equivalent to A. So, A is row equivalent to B if and only B is row equivalent to A. This is called the symmetry property of row equivalence. And the third, if A is row equivalent to B and B is row equivalent to C, then A must be row equivalent to C. This property is called transitivity. So, the row equivalence has these three simple properties which makes it a equivalence relation. So, row equivalence is an equivalence relation on all m by n matrices, on the set of m by n matrices. Now, if you have a matrix A and A is row equivalent to B, That means we can go from A to B by a sequence of elementary row operations, a finite sequence of elementary row operations, but we have seen that the elementary row operations do not alter this set of solutions of the homogeneous system, and therefore, what we obtain in the end B will have the same set of solutions for its homogeneous system as A. So, A is rho equivalent to B implies A x equal to theta m, the homogeneous system corresponding to A, and B x equal to theta m, the homogeneous system corresponding to B, both have the same set of solutions. Both have the same set of solutions. So, instead of solving the system A x equal to theta m, we could also solve the system B x equal to theta m. So, what is our main strategy for solving homogeneous systems? Given the matrix A, you find a matrix B such that 1 A is rho equivalent to B, so that A x equal to theta m and B x equal to theta m have the same solution, and B x equal to theta m is easy to solve. If we can do this, then we can solve the B x equal to theta m, and since the solutions are the same as the solutions of A x equal to theta m, we would have found the solutions of the given system A x equal to theta m. So, the question therefore is, what are some easy B's? In other words, what are such B's for which the system is easy to solve, and then how to reduce A by EROs to easy B's. These are therefore the fundamental questions in solving homogeneous system. We shall look at the first question, what are some easy B's? So, let us look at a simple example. Consider the matrix A 0 0 1 0 0 0 0. This is a matrix with 4 rows and 5 columns. So, it is in F 4 by 5. So, we have matrix which has 4 rows and 5 columns. Let us look at some basic features of this matrix. This matrix has been written in such a way that it has some special structure, some special features. Now, we are going to look at some of these special features. What are these special features? The first thing that we observe is that the matrix A has some rows which are all zeros and some rows which has non-zero entries. So, we have the matrix has rows in which all entries are 0 and such rows are called 0 rows. Now, obviously, therefore, if a matrix has non-zero entries, it is called a non-zero row. Non-zero row is a row which has non-zero entries. So, the first thing we observe is that the matrix has 0 rows and non-zero rows. In this example, the first row, the second row and the third row are the non-zero rows, and the last row, the fourth row, is the 0 row. So, in this example we have R1, R2, R3 are non-zero rows and R4 is 0 row. So, that is the first simple thing that we can have in a matrix. Some rows will have all zeros, some rows will have non-zero entries. And the most important thing structure in this, the first starting point is that the row which has all 0 entries comes after all the non-zero rows. The non-zero rows appear on top and then come the series of 0 rows. So, the first important feature therefore is the 0 rows all appear below all non-zero rows. The 0 rows all appear below all non-zero rows. That is the first important feature that we observe. The second important feature is, let us get back to that matrix again. We will see that in every non-zero row, take the non-zero row, there must be a non-zero entry. For example, here in this row the non-zero entry is 1, in the second row the non-zero entry is this one, and the third row the non-zero entry is this one. So, therefore, in each row there is a non-zero row entry, first non-zero entry, and that turns out to be 1. Here it is 1, here it is 1 and here it is 1. So, the important observation is that the first non-zero entry, when we say first, we mean the first when we read from the left of the matrix, left entries from the first column onwards. The first non-zero entry in each non-zero row is 1. This is called the pivotal entry of that row. So, every non-zero row has a pivotal entry, and that is 1, and that appears first from the left side as the first non-zero entry. Now, let us get back to that matrix again. We will see that the pivotal entry here is 1, and if you go down to the next row and if you want to locate the pivotal entry, it has moved to the right, and if you want to go to the next non-zero row and look at the pivotal entry, it has moved to the right. That means, if you take two non-zero rows Ri and Rj, then if I is less than j, then the pivotal entry of the ith row appears to the left of the pivotal entry of the jth row. So, in other words, the important thing that we have to observe is that if Ri and Rj are non-zero rows and the pivotal entry of Ri appears in kith column and pivotal entry of Rjth row appears in kjth column, then I less than j, that is the R I row appears above the R j row, implies k I is less than k j, that is the pivotal entry corresponding to R I appears in a column to the left of the column in which the pivotal entry of R j appears. This is the third important property. Then the fourth important property that we observe is the following: pick up this pivotal entry 1, all the entries below that are 0. Look at the pivotal entry in the second column, all the entries in the second row corresponding to the pivotal entry which is in third column, all other entries are 0. Similarly, the third pivotal entry which is in the third row fifth column, all other entries in that column are 0. So, we make that point and we observe the fourth important property of this matrix is, if a column contains a pivotal entry, then all other entries in that column are 0. All other entries in that column are 0. So, a column with suppose a pivotal entry would have had all the other entries as 0. There will be a one standing alone in that column, all others would have been made 0. Similarly, for example, in our example we had the first row, the pivotal entry was in the first column and all other entries in the first column were 0. The second pivotal entry which appears in the second row is in the third column and all other entries in the third column are 0. The third pivotal entry which appears in the third non-zero row, namely the third row, is in the fifth column and all other entries in the fifth column are 0. So, these are the basic features, namely there are non-zero rows and 0 rows. All the 0 rows appear after all the non-zero rows. The first non-zero entry in each non-zero row is 1 and these are called pivotal entries, and as we go down the matrix the pivotal entries keep moving to the right, and any column which contains a pivotal entry, all other entries are 0. Whenever a matrix is in this form, it is called, whenever a matrix is in this form, it is called a row reduced echelon matrix. So, a matrix which has these properties these 4 important properties is said to be in row reduced echelon form, and such a matrix is called a row reduced echelon matrix. We will simply write RRE, row reduced echelon matrix. So, in general, so if we consider a matrix B which is in FMN and if it is in RRE form, what are the features? Then we mean that it is in RRE form. Let us say R1, R2, R row are the non-zero rows. Since they appear always, the non-zero rows appear on top, they will take all the first few indices for the rows and then the remaining rows are the 0 rows, R row plus 1, R row plus 2 up to the mth row or the 0 rows. So, it will have say row non-zero rows, they will all appear on top and it will have m minus rho 0 rows, they will all appear at the bottom, that is after the 0 rows. The next important property is the first non-zero entry from the left. The first means from the left. The first non-zero entry in each Ri is 1 for 1 less than or equal to I less than or equal to rho. The first rows are the non-zero rows, and the first entry is always 1 in these non-zero rows. Now, where do this appear? So, suppose Ri has its first non-zero entry in column Ki. The column index is Ki. What does that mean? That means if you take the matrix, this is the ith row, that is non-zero, and this is the kith column, and that must be 1, and all the entries before that must be 0. That means B I j must be 0 for j equal to 1, 2 up to k I minus 1, and then when I came to k I get a 1. So, this is what we mean by saying the Ri has its first non-trivial entry in the kith column. Then we have observed that the non-zero entry 1, the pivotal one, keeps moving to the right. So, if I is less than j, the column in which the first non-trivial entry corresponding to row I appears in Ki, the first non-zero entry corresponding to row j appears in column Kj. Since they keep moving to the right, Ki must be less than Kj. So, the pivotal ones, as we go down the matrix, the pivotal ones keep moving towards the right. And supposing we have the ith row and we have the pivotal one in the kith column, we should have all the entries in the pivotal column other than this one to be 0. What does that mean? If you look at the kith column and if you look at any row j, that must be 0 if j is not equal to ki. That is, this must be 0, that is B1 ki, B2 ki must be 0, and so on. When you hit ki, you must get 1, and again when you go out of ki range, you must get 0. So, the column supporting the pivotal one must have all other entries. So, this is the general structure of a row reduced echelon matrix. Now, the question is, what good is such a row reduced echelon matrix? It is easy to solve the homogeneous system Bx equal to theta m if B is in row reduced echelon form. We shall see this fact now. Let us first illustrate this with an example. This is the same example we started with. This is again a matrix which has 4 rows and 5 columns. Now, as we had already observed, this matrix is in row reduced echelon form. So, let us look at how the homogeneous system looks like in this case. If you look at the homogeneous system corresponding to this, it is x 1 plus 2 x 2 plus x 4 equal to 0. That is the equation corresponding to the first row. The second row x 3 plus 4 x 4 equal to 0. The third row gives x 5 equal to 0. The last row gives just 0 equal to 0. So, effectively therefore, there are only 3 equations. So, the number of effective equations is equal to the number of non-zero rows in that row reduced echelon form. Now, let us look at this system. The variable corresponding to the first pivotal entry is x 1. The variable corresponding to the second pivotal entry, it appears in third column and therefore, it is x 3. The third pivotal entry appears in the fifth column and therefore, the variable corresponding to that is x 5. So, the column index of the pivotal entries give us what are known as the pivotal variables. So, the variables corresponding to the columns in which the pivotal variables, the pivotal ones appear are called pivotal variables. Thus, in this example, the pivotal variables are x 1, x 3, x 5. So, x 1, x 3, x 5 are the pivotal variables. Obviously, the other variables, there are totally 5, the remaining variables are x 2 and x 4, they are called non-pivotal variables. Notice that the number of pivotal variables is equal to the number of non-zero rows, and the number of non-pivotal variables is the remaining, totally there were n. So, therefore, it is n minus number of non-zero rows. Now, let us get back to the system. We have now identified these 3 pivotal variables. The important fact is each one of these pivotal variables appears exactly in one equation. The pivotal variable x 1 appears only in the first equation, the pivotal variable x 3 appears only in the second equation, the pivotal variable x 5 appears only in the third equation. Therefore, we can eliminate the pivotal variable x 1 from the first equation, and when we eliminate, the remaining pivotal variables will not appear, because each equation has only one pivotal variable. That x 1 can be eliminated in terms of x 2 and x 4, the 2 non-pivotal variables. In the second equation, x 3 helps you the second equation helps you to eliminate x 3 in terms of non-pivotal variables, and the third equation eliminates the pivotal variable x 5. So, the ith equation eliminates the ith pivotal variable, k ith pivotal variable we should call it, pivotal variable in terms of non-pivotal variables. So, therefore, in this example we have x 1 is eliminated in terms of x 2 and x 4, x 3 is eliminated in terms of x 2 and x 4, x 5 is eliminated in terms of x 2 and x 4. Let us go back to the system again. the first equation gives us the x 1 as minus 2 x 2 minus x 4, x 3 as minus 4 x 4 and x 5 is 0. So, we have x 1 equal to minus 2 x 2 minus x 4, x 2 equal to minus 4 x 4 and the x 3 x 5 equal to 0. Now, whatever values we choose for the non-pivotal variables x 2 and x 4, as long as we choose x 1 and x 3 and x 5 as per this rule, then the system is going to be satisfied. So, any solution is of the form x equal to, you can choose, you have to choose x 1 as minus 2 x 2 minus x 4, x 2 any value you can choose, x 3 should be minus x 4, x 4 can be any value, x 5 can be this. So, thus the solution by varying the x 2 and x 4, we get all solutions. So, therefore, the moral of the story is, if a matrix B is in RRE form, suppose we have a matrix which is in row reduced echelon form, let us describe it. R1, R2, R row are the non-zero rows, R row plus 1 etcetera Rm are the 0 rows. Suppose we have a matrix in row reduced echelon form and we have row non-zero rows and n minus m minus row 0 rows. Now, each non-zero row produces a pivotal variable. Where does it come from? It locates the column in which the first non-zero entry, that is, let the first non-zero entry, that is the pivotal one, in row Ri appear in kith column for 1 less than or equal to I less than or equal to rho. For rows beyond row, there is nothing like non-zero entry because all the entries are 0. So, the rith row has the non-zero pivotal 1 in the kith column. So, corresponding to this, the ith pivotal variable will be xki. So, we get all the pivotal variables as xk1, xk2 and so on xk row, and xj for j not equal to k1, k2, k row are the non-pivotal variables. So, if you have a matrix B which has m rows and n columns, the out of the n pivotal variables, row or out of the n given variables, row are pivotal variables, where row is the number of non-zero columns in that row reduced matrix, and the remaining are all non-pivotal variables. And xk1, xk2, xk row, the pivotal variables can be eliminated in terms of the non-pivotal variables. This is the general strategy for solving systems of equations, homogeneous systems of equations when a matrix is in row reduced echelon form. And when we eliminate in terms of non-pivotal variables, the non-pivotal variables can be chosen arbitrarily in F. By varying over all the possible values that we can choose over F, we get all the solutions of the homogeneous system. So, the general strategy therefore, for the matrix when it is in row reduced echelon form is fairly simple. Therefore, the question is, given any matrix A which is m by n, can we find a matrix B which is in also an m cross n, 1, 2, it is row equivalent to B, and 3, B is in row reduced echelon form. So, given a matrix A, we want to find a matrix B which is of the same size, which is row equivalent to A and which is in row reduced echelon form. Why do we ask this? Then the system, homogeneous system Bx equal to theta m has the same set of solutions as Ax equal to theta m. The reason is they are row equivalent, and we have seen that when you have two matrices which are row equivalent, the corresponding homogeneous systems will have the same set of solutions. So, Bx equal to theta m has the same set of solutions as Ax equal to theta m, and Bx equal to theta m is easy to solve because B is in row reduced echelon. We have just seen that if a matrix is in row reduced echelon form, we have a systematic way of eliminating the pivotal variables in terms of the non-pivotal variables and choosing the arbitrary values for non-pivotal variables over the entire F, we can recover all the solutions for the homogeneous system and thereby getting the solutions of Ax equal to theta m, because now as observed above, the Ax equal to theta m system and the Bx equal to theta m system both have the same set of solution. So, therefore, the general strategy will be to get such a B. Can we find such a B? And the answer is yes. And we shall see how to find such a B. Now, obviously, since we want A to be row equivalent to B, somehow or the other we must be able to move from A to B by elementary row operations. We should be able to find a finite sequence of elementary row operations, because we want to move from A to B in a finite number of steps. A finite sequence of elementary row operations, say E1, E2, Ek, such that when we go on operating this, first you operate the row operation A1 to go to A1, then operate E2 to go to E2 and so on, and finally operate Ek to get Ak, and my Ak must be equal to B, which is in row reduced echelon form, which means we must start with the matrix A, develop a sequence of elementary row operations step by step in such a way that after a finite number of steps we end up with a matrix which is in row reduced echelon form. And since we have moved from A to this by only elementary row operations, this row reduced echelon form will be row equivalent to A, and therefore, instead of solving Ax equal to theta m, we can solve Bx equal to theta m. How do we do this? We shall now look at this reduction process. That is the process of finding these elementary row operations which will eventually take us from A to a row reduced echelon form in a finite number of steps after a finite sequence of elementary row operations. And we shall see it is a very simple operation. Essentially, we will be repeatedly applying one particular idea, and we shall describe this. So, the first basic operation, we shall call it the first column operation. The first column operation FCO. This what we mean is, obviously it is an operation which we are going to perform on column. Which column? The first column, and obviously we will be talking only about row operations. So, it will be an elementary row operation. So, it is elementary row operation applied, it may be a number of them, applied to the first column of any matrix. Given any matrix, we apply this operation on it. It is a set of operations, all of them are elementary operation. So, what is this operation? So, we will call it as FCO, the first column operation. Start with any matrix K which has P rows and Q columns, any general matrix P by Q. Once you are given this matrix, we first ask the following. Since it is going to be operating on the first column, we look at the first column and ask this question: does the first column have a non-zero entry? We ask the question, does the first column have a non-zero entry? So, if we are given any matrix, we just focus on the first column and see whether everything is 0 or somewhere somebody is non-zero, somewhere some entry is non-zero. So, obviously, we will get two types of answers possible for this, yes and no. Now, we shall describe what we shall be doing if the answer is yes, and what we shall be doing if the answer is no. If the answer is yes, what it means is there is a non-zero entry in the first column, it may be on top or the top entry may be 0, the next entry may be also 0, somewhere there will be a non-zero entry. If it is already on top, do not worry. If it is not there, there will be somewhere else a non-zero entry, bring it to the top. How do I bring it? You have to do only a row exchange. So, bring a non-zero entry. When we say top, we mean the leading position, first column, first row to the leading position. We may have to use an elementary row operation of interchange of rows to achieve this. If necessary, using ERO of type 1, which is the row exchange. So, the first step in this operation is scan the first column, see if there is a non-zero entry. If there are non-zero entries, bring one of them to the top position if necessary by using row exchanges. Now, we may ask, when there are many non-zero entries, which one should I bring? Theoretically, it is irrelevant which non-zero entry we bring to the top, but in computational methods, from the point of view of error control, it is always better to bring that entry which has the largest magnitude to the top position. Now, having brought that entry to the top position, it may be 46, it may be 32, it may be -5, it may be √2, some non-zero entry has come to the top. We would like to have a standardization there. We shall make that 1. How do I make that 1? If it is already 1, I do not have to do anything. If it is 15, in order to make it 1, I will divide it by 15. What does that mean? You have to multiply that top row by 1 over 15, and that is an elementary row operation of type 3. So, if necessary, use ERO of type 3 to make this top non-zero entry as 1. So, now what we have achieved is, we have looked at the first column. In the first column, we have now brought a 1 to the topmost position. Now, below that 1, there may be zeros, there may be non-zero entries. Now, we have standardized, we will clean up and make all the entries below this 1 as 0. In order to do that, all we have to do is multiply a suitable multiple of the first row and subtract from here. Suppose we had a 4 in the 4th row, then we multiply the first row by 4 and subtract, we will get a 0. Make all entries below this 1 as 0 by ERO type 3. Now, when we do that, the first row, first column would have become like this. We have brought a 1, we have brought some non-zero entry to the top, made it as 1 and brought everything else as 0, and then there will be all kinds of entries here, and this sub matrix we will call as K1. This is what we do in the first column operation. If the answer is no, if the first column did not have any 0 entries, we do nothing. Then the matrix will be of the form 0 0 0 0 first column, and what is remaining there we will call as K1. In both the cases, the matrix K1 when we got in this situation and the matrix K1 we got here, both are one column less than what we started with. We had an P by Q matrix, now these people will have Q minus 1 columns. The first stage of this reduction operation is this first column operation, which brings the first column to a standard format where all the entries are 0 as is shown here, or all the entries are 0 as below the 1 and the topmost pose is 1. So, one of these two formats is the standard format that the first column operation brings the matrix to. Now, what do we do from this stage on? That is the next stage of the reduction process to row reduced form, which we will look at in the next lecture.